Yeah. Okay, well, welcome back to part three of the Nystrom and random Fourier feature series. So here in the last lecture, I think we talked about Nystrom, and basically the idea is if you have a very large matrix, what you could do is divide the matrix into four partitions, and by essentially calculating a bunch of things using the partition A as well as calculating B, you're able to obtain the rest of the matrix. So that's the first way which we can use Nystrom. And there's another way which is also very useful. Notice how calculating the matrix is already really complicated. Imagine if we had to find the eigenvectors of this matrix. So now I think you've done PCA and LDA, so you can imagine finding an eigenvector is very often the solution of a problem, right? Finding so that's the solution. Then what if the matrix you have turns out to be really really large, right? For PCA, what if this is really large? So what would you do then, right? How would you then calculate the eigenvector if it's super big? So the second way to use Nystrom is essentially to use the eigenvectors of A to approximate the eigenvectors of the entire matrix K. Okay? So that's the second way. So larger matrix could be very, very expensive, and the eigendecomposition process, finding the eigenvector, has big O notation and a cube. This implies that as the number of sample increase, the computation required is cube, which is three times. It's not three times. It's like whatever n number of samples you have, cubed amount of computation. So it grows very quickly. It's very, very expensive. And since eigendecomposition is useful for PCA, LDA, spectral clustering, etc., a lot of things requires eigendecomposition. It would be really helpful if we have a way of approximating the eigen vectors of very large matrices. And using what we learned from Rosasco, then we can actually then combine that with what we have with Nystrom, essentially do this. Okay, so from Rosasco, well, exactly same thing. If we just take the matrix A after we shuffle them, we can essentially get the eigenvectors. And Rosasco tells us that if you know the eigenvectors, we can get the eigenfunctions, right? So this is the first step of Nystrom that we did last video. So so if we know the eigenfunctions, well, that means the second part of Rosasco tells us that if we know the eigenfunctions, we can get the eigenvectors back. So what's happening is if we can get the eigenvectors of A, we can get the eigenfunctions of K, right? Approximately. And once we have the eigenfunctions of K, we can get the eigenvectors of K back using the second one, right? The only difference here is when you're trying to get the eigenvectors of the entire matrix, instead of phi A, you're going to use phi, right? Because phi has n samples. So you're using the entire phi. And that's it. That's it. And all we have to do now is to combine the algorithm. So here you approximate the eigenfunctions use A, and then you plug it in, right? So let's plug this in. Right? I'll plug this in here, resulting in this, right? Well, the square root of sigma, that's the eigenvalues of A. Well, they're constant, so you can multiply them together. So it's one over the sigma, and then phi and phi a multiplies together. We saw already what this means. This was this portion, which you call it Ka, which we also call it L. The traditional Nystrom literature calls it L. And therefore, this right here is just L, and you can approximate the eigenvectors of the entire matrix K simply by multiplying the eigenvectors of A, so this came from A, by L divided by sigma, and voila, you have it. It's almost magic. Of course, I need to keep caveat. If A is too small, A has to be big enough, right? If A is too small, then A is not a representative K, then it's not going to do a good job. So depends on the data. If the data is huge, then you can pick a proportionally small A, and you will be able to do it. But if the data is already very small, then it's not really worth it. Okay, so this right here will, if you have the ith eigenvalue and ith eigenvector, you can find the ith eigenvector of K. Okay. Now, if you want to find more than that, you can do this again. So this will be the first one. The second one, right? You can get the second eigenvector, and you can do it again. 1 of sigma 3 L V 3. So you can essentially get all the eigenvectors this way, as shown here, right? And when you do that, then you can pull L outside because L is all the same. So L outside, V and sigma. So notice how you can pull the sigma out. So once you pull everything out, I'm going to call this matrix L. I'm going to call this V hat. I'm going to call this sigma inverse. So you can get multiple eigenvectors simultaneously using this. This tells you how to find the eigenvector of one eigenvector. This tells you how to find the eigenvector of multiple of them. Okay. Now I wrote the code to show you. In this particular example, I didn't use a very large data. I think I only used 170. So if you use 30 samples, it didn't do a good job. Like it's the approximation. And if I use more, it did a pretty good job. You can see that the actual and the approximation pretty close. So this is specific to very large number, and 170 wasn't very large. So I recommend you try it with a larger one. Okay. So this is part 3, and in the next lecture, next part, we'll talk about random Fourier feature. Okay.